Welcome to another session of Artificial Intelligence Foundations and Applications. Today we'll be looking into Prolog programming. This is primarily based on uh, predicate logic that we have seen. So, some of the problems in predicate logic can be translated into Prolog programming. So we'll be looking into that, how to do the same step and what are the other things that Prolog supports. So just to start with, this Prolog, it was invented in early 70s by these fellows, uh, and it's become popular at a later stage because of it has lot of applications in different domain. So this Prolog was basically derived from the stuff, so which is effectively means programming in logic, that is in English. So one of the major thing that you need to know about Prolog is that it's a kind of a declarative programming language, unlike the most common programming language. So when we say it's a declarative programming language, it is something else that it is something else that is not common for the other programming language like C and C++, where we write the steps that needs to be followed in sequence. But in case of Prolog, it is not the same. We write a few set of rules and facts, and we give it to the system, and the system will try to figure out any solutions for that stuff. So typically for a declarative language, the programmer specifies a goal to be achieved, and along with the set of information that it needs to provide, and the Prolog system works out how to achieve it. So in purely declarative language, the programmer only states what the problem is and leaves the rest to the language system. But in case of when we solve any problem C and C++, then we explicitly specify what are the steps needs to be followed, in what way it should execute. So it follows a sequential execution, and we try to fit in that way. So when we talk about Prolog, so we need to think of a notion called relation. So because the predicate logic that we have seen earlier, uh, which is also specifies some kind of a relation. So so which is the relation between objects, or maybe the properties of the object. So like say, what when we can say that Aisha owns the pen, then we declare ownership between Aisha and the pen. So if somebody asks, does Aisha own the pen, then we are trying to find out about a relationship between Aisha and the pen. So the relationship can be, think of a rule also. For example, if we try to specify the relationship of sisters, so two people are sisters if they are both female and they have the same parent. So we are so this relationship that we are specifying, it's a kind of a generic one. We are not uh, looking into two people explicitly here. But in traditional programming language, the same relationship can be defined in this manner. Like I take two instantiation like A and B, they are sisters if A and B both female and they have the same father and they have the same mother, and A is not the same as B. So this is an explicit declaration of the relation, and here we try to uh, define the relationship in a generic way. So a rule allows us to bind about the relationship even if the relationship is not explicitly stated as a fact. So this is the one of the major difference between the traditional programming language and the Prolog programming. So to write a program in Prolog, or what we need to do in a very broad sense, we have to describe a set of facts which we have to describe the set of facts which basically describes the relationship between the objects and or the properties of the object. Like if I say Shubot likes pizza, then I can probably specify likes Shubot pizza. So which is a kind of a ground fact, and uh, uh, that is the relationship between Shubot and pizza, and, and or maybe or when sky has color blue, I am specifically specifying one of the properties of the object. So so this is one of the thing that we have to specify a set of facts, and the other things is kind of a rule where we implicitly specify the relationship between objects, or it's a kind of a object properties. Like x is a parent if there is a y such that y is a child of x. So here we are basically specifying a relationship using a set of rules. We are not explicitly specifying the object for which we are seeing this relationship. And once we have this, then the system can be used by asking a question relationship between the objects or about the object properties, like does Shubhat like pizza, or is Aisa a parent? So this kind of queries that we have seen in case of predicate logic, we can actually do the similar stuff here. So so in order to uh, say few things about Prolog and the predicate logic, because Prolog is basically based upon the predicate logic, but there are few things we actually need to know. So just quick summary. So Prolog is a programming language based on the predicate logic. So it Prolog program attempts to prove a goal. So if somebody asks me Barney, so brother Barney and X, then we from the given set of fact, we would like to find out the set of X which actually fits to this query. So what we need to do in when I have a query something like this, we the Prolog tries to use the substitution and the other kind of mechanism, and then it tries to infer whether this is true or not. So here uh, we go so in Prolog we go for a substitution, and we try and we use the other rules of inference to find out the final to check whether the goal is hold, or we cannot prove that goal. So so the question then it can be asked that how does Prolog know which facts and which rules to use in the proof? So Prolog has a very simple thing. So it uses unification stuff. It applies the unification steps to determine when the two clauses can be made equivalent by substitution of variables, and then unification procedure is used to instantiate the variable in a goal clause based on the facts and rules in the database. So we will elaborate these two steps with some examples at a later slides. So the main idea is that we try to do unification, and we try to instantiate variables so so that that matches with the clause or the facts and the rules of the database or the knowledge base that we have been provided with. So let us look into a very simple program. So so we have been given a set of ground facts, so which are male Albert and male Edward, female Alice, female Victoria, parent Albert Edward. So Albert is parent of Edward, Victoria is parent of Edward. Now we are defining the rules in this way. Father xy, so x is father of y if x is parent of y and x is a male. Similarly, we are defining another rule, mother xy, so x is a mother of y if x is a parent of y and female x. So this is the top part is the ground facts, and these are the actual rule that we are defining here. Now in terms of the predicate logic, so these are the normal predicates where we are specifying the ground truths or the ground facts, and for the rules there's a implicit rules for the so these are the rules, and for these rules there is an implicit quantification. So what is that? So when we write a statement something like this, father xy, parent xy, male x, in Prolog, it effectively means that for all x, for all y, parent xy and male xy implies father xy. So if we so when we write this sentence in Prolog, it effectively means in terms of our predicate logic that there is an implicit for all x, for all y, and the right hand part of this expression implies the left hand part. And in case of Prolog, so here only I can have multiple so I can have set of set of conjunctive elements here, but on the right hand part there will be only one element. We will see what kind of statement is actually being supported here. So the thing is, when for any rules it will be something like something implies something, and on the on the implied part there will be only a single element. We cannot have more than one element on this part. Similarly for mother xy, so for all x, for all y, parent xy and female x actually implies mother xy. So on the right hand part there will be only one element. Similarly, if we look into the Prolog, so this will be called the rule head, and on the rule head there will be only one predicate. Now with respect to Prolog, we would like to mention few syntax here. So any fact or rules or statements actually ends with dot, and white space are actually ignored. So this symbol, when we have this colon dash, this is this is actually can be read as kind of a if, and the left hand part of this expression is called the rule head. So we say that x is father of y if the right hand part holds, and this comma that we have in the body, which is actually a logical and anything that follows the percentage symbol, that can be treated as a comment. So what we are talking about, like when we write a Prolog program, it basically maintains a set of facts and rules in its knowledge base. So facts are actually basically axioms. So it basically defines the relationship between terms that are assumed to be true, and rules are the basically theorems that allow new inferences to be made. So something like male Adam, female Anne. So these are my facts, and I am just defining few rules, and using these rules, certain relationships can be derived uh, from the knowledge base. So the stuff that we have already talked about, like when we write these rules, so it effectively means that for all x and y, x is the son of y if there exists x and y such that y is the parent of x and x is male. So we can write it in the first order logic in this form. Similarly, we can actually write the second rule, like uh, x is the daughter of y. So for all x for all y, x is the daughter of y if y is a parent of x and x is a female. So parent yx and female x implies daughter xy. So when we talk about this prolog and predicate logic, so Prolog actually supports this predicate logic in a little bit simplified form, and this simplified form is known as horn clauses. So so what is that? So statements are constructed from terms, so that there is the basic thing, and and each statement that we construct or the clause has at most one term on the left hand side. So this is with respect to Prolog. So the rule head will be only a single term, or if we say in terms of the predicate logic, then it will not be a left hand side, but it will be a right hand side stuff of the implication. So here what we can say, so for a Prolog statement or the rule, so it will be at most one term on the left hand side of the implication symbol. So with respect to Prolog, this is our implication symbol, and each statement has a conjunction of 0 or more terms on the right hand side. So which we have seen that on the right, so every so it's a so it's a conjunction of terms, and that is separated by commas. So the Prolog has three kind of statements corresponding to the structure of horn clause used. So it's the one is the fact, so which is the simple uh, ground truth, so which does not have anything on the right hand side. Then a rule which has which is a clause on both the sides, and there will be a questions on the goal that we have not seen yet. So goal is a clause with an empty left hand side. So fact which do not have anything on the right hand side, question which has the empty left hand side, and a rule which has uh, which has terms on both the sides. So let us look into how we can execute a program. So the example that we are talking about earlier, so given a set of facts and given a set of rules, we would like to query some of the stuff. So uh, in order to run this Prolog program, we need to have a Prolog compiler or the Prolog interpreter. So GNU actually comes with a free tool called Prolog, which has a compiler called GPLC. So, so what we need to do is we need to write this program in a file. Let's say I have written this program in a file named say family.pl. So if I run GPLC on this file, it will generate an executable called family, and then if we execute this family executable, then it will give me a prompt something like this, which basically means that I can it gives an interactive cell where I can type my queries and I can get my answer. So for example, if I type male Albert, it will say it's true because because it can actually derive from this term that male Albert is true, so it will write yes. So if I ask male Victoria, then since so Victoria is never comes with male, so definitely this is no, so it will say no. And if I ask male Subodh, since Subodh is not in its database, so it will say no. Now another interesting thing is, like if we ask male X, then it will return me the whatever uh, whatever variables that matches with X and that makes the male X to be true. So from our knowledge base we have two such things. So X can be Albert, X can be Edward. So we will get all the matches as an answer. So, so if you are interacting with Prolog or this stuff, then if you type male X, then it will prompt you X Albert and with a question mark, then you have to type this semicolon, which means that it's a kind of a no match, so or the match that I'm not looking for, so you try to figure out the other match, or in other sense we can this can be interpreted as it is trying to find out, or I'm saying this interpreter find out the other solutions. So so it will basically print these two things. So the question is, when we write this stuff, so I missed a dot here, so there will be a dot in this part. So when we write male X, or my query is male X, it effectively means that I am asking a question something like this. So does there exist X? Male X is true. So when we define these rules, there is an implicit for all X stuff, and when I'm asking some query, so it is implicit uh, there exist. Similarly, I can ask a query like if father X sorry, so it's a father if and father F and C, so which is effectively means that I am asking the system a query: does there exist F, does there exist a C such that F is the father of child C? And if we ask this query to the system, then it will print F equal Albert and C equal to Edward. And if we try to ask for more solution, then it will find out no such solution, and then it will print no. So you can use Prolog, and you can actually write this code, and you can actually play around with this stuff. So in Prolog, the implication rule is from right to left, and the scope of a variable is the clause in which it appears. Variables whose first appearance is on the left hand side of the clause has implicit universal quantifiers, and variable whose first appearance is on the right hand side of the clause have an implicit existential quantifiers. So now with respect to Prolog, so in Prolog we can define the separate stuff, like we can define the constants uh, which can be an identifier. So identifier is a kind of sequence of letter digits or underscores, but that starts with a lowercase letters. So that is the typical stuff it is followed in Prolog. We can have number and we can have strings enclosed in the single quotes. So strings can actually start with uppercase letter and can be number also, and now treated as a string. So if it's a given within a single quote. So for variables, it's also a sequence of letters, digits, or underscore that starts with an uppercase letter. So that is the distinction between the constant and the variable, or an underscore stuff. So when we have a underscore only, it by itself it's a kind of an anonymous variable, so it just has a special meaning. So the other important thing in Prolog is the structure that we would like to define. So like we can define something like a structure is kind of a date which we'd like to specify say uh, date is 20 and April uh, 20th April 2020. So that is my definition of my structure, or I can define a points in 3D plane. So this date is an identifier, and then I can have few terms within it. And this kind of definition can be recursive. I can explicitly specify, or I can specify the dates in this manner. So it's effectively means that I need to do an addition operation before I use the first term, so which is effectively turn out to be 20. So so this structure can be actually represented as a tree as well. The another important thing in the Prolog is the list, so which is very useful data structure. So list are the structured terms represented in a special way. So I can represent a list in this manner. So it will be represented within the third bracket and the set of elements. And interesting thing that this structure can be uh, represented in this manner as well. So what does it mean? First of all, this part, when I am specifying something within the third bracket, it is basically denotes a list, and in this case this list is an empty list because no elements is there. And in each list we can actually represent the list in this form. So it has a head and it has a tail. So the list consists of head and tail. So head is an element of uh, of the list. It can be a list but not necessarily a list. Similarly, tail is a list or it can be a sub list. So therefore, when we have this A B C D, we can actually represent this structure item in this manner. So this is my head and this is my tail. So A is my head and the rest of the list is another list consists of B, C and D. Or I can see this is my head. So A is my head and the this part is this list B, C, D. I am representing B as a head and C and D is the tail part of it, and similarly and so on. So we can represent in this manner as well. So this structure has an important implication when it comes to matching variables against list. We will see how to do that. So predicates, which is required to specify the first order logic, which has the similar syntax like the structure, which comes with a kind of a identifier and followed by the terms. And we can basically specify the ground facts, we can specify the rules with variables and so on and so forth. So here when we say like x is a variable, x can take any term as the value, so that makes this likes x to be true. So when we specify these facts, is basically we are making an assertion, that means these are the ground truth. So so the rules that we have seen earlier in a more uh, formal form, rules will have a rule head or the predicate head. This is the reverse implication sign, and this is the term that need to be separated with logical and, which we represent is using a comma. So this predicate head is the rule head, and when I specify a rule, it ends with a dot as per the Prolog syntax. Rules are basically the encoding for deriving the computing the new facts. Like if we specify animal x, if x is an elephant, so x can be concluded to be an animal if I can show x is an elephant. Similarly, if there is a rule like taller than xy, then I can say x is taller than y if I can show that the height of x, which is h1, and height of y, which is h2, and h1 is greater than h2. So I can claim these to be true if I can show the right hand part is actually true. Similarly for this ones, father xy, parent xy, and male xy, so I can say this is true if I can show that this part is being hold. So 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 we basically we need to uh, when we try to query the system, we need to derive this in this stuff, and we will be using these rules to derive certain facts, so which we call the kind of operations on of Prolog. So the query will be that we would like to ask the system. It will be a set of predicates which will be separated by comma, that means it's logically ended, and Prolog tries to prove this sequence of predicates using the facts and the rules that have been defined. So how it's being done, we will elaborate with an example. So let's say we have been given this set of information. So these are the ground truth, and these are my set of rules that have been specified, and this is my query that I would like to see whether this is hold or not. Now when we do these operations, the idea is as follows. So for a generic example, like say I have been given this rule, and I have been asked to check whether this query is satisfied or not. So what we do, so Prolog starts the first predicate, so it looks into the query, it takes the first predicate p1 in our case, and then it examines the program from top to bottom. So there can be many such rules, and so it will start from the top, and whenever it finds a match, it cho- choose that rules. For our case here it's on the single rule, so it will match with this one. So the match means I take the predicate p1 and I check with the rule head of this rule, and I see that if there is a match, so I will take that rule. So if it matches with the rule head, then what it does, it replaces this predicate p1 with the rules body that have been provided to me. So if p1 is matched a fact, uh, uh, so if p1 is matched, then we replace this p1 with the uh, rule body. So effectively when p1 matches with the rule, therefore the new query that I need to check is this one. So I'll replace p1 by q1, q2, q3, and p2, p3 will remain as it is. So this is when p1 matches with a rule, and if p1 is matched to a fact, then we can think of the facts as having an empty body, because it has nothing, so it's a ground truth, so it is true, so we can actually remove that stuff. So let's say if p1 is a basic ground truth, then effectively my new query will be p2 and p3, because there will be nothing to replace here. So we will see with a concrete example. So the examples that we are talking about earlier, so we have this ground truths, we have these rules, and we have our query. So when we get this query, animal Fred, animal Mary, animal Joe, so we choose this predicate animal Fred, and we will search from top to bottom. uh, so we can search in different ways, but the Prolog follows in that manner. So the compiler typically use, or the interpreter follows these notions. It will start matching from the top. So here I can see one match animal Fred. So this animal Fred will be replaced with the right hand part of the rule body. This is elephant Fred, and rest of the term will remain same. So we will get this stuff. Now we have this animal elephant Fred, and elephant Fred actually matches with this ground fact, and it does not have anything on the rule body, so we can simply remove this part because this is being matched. So now we have to evaluate animal Mary and animal Joe. Again, for animal Fred, it does not, though it match, but Mary and Fred does not match, so this rule will not match. Animal Mary and this animal Mary will match, so it will be replaced by elephant Mary, and animal Joe will remain as it is. And elephant Mary, again it will match with the ground truth, so we will remove elephant Mary, and we will have animal Joe. And if we continue to do so, at some point of time we will reach elephant Joe, and there is nothing to check, or I have an empty query. So when I get empty query, I can say it is actually true. So if this operations, or if this process reduces to a query empty, reduces to a query to the empty query, then Prolog returns the returns yes. So that means it's true. And if it does not match with any one of those things, then it will return false, or it will respond with a no. So in during this process uh, of the matching, so if the predicate in the query might match more than one fact or one rule head, then Prolog always choose the first match it finds, and then if the resulting so it will choose that match and it will try to check whether it holds with that assumption or not. If if it finds that the resulting query did not match or did not succeed, then it will try to backtrack and try to find a new match, and then it will continue. So it will select gradually one by one. So for example, let's say I have this ground truth and two rules, and our query is animal friend. So animal friend, it will match with the first one. So this animal friend will get replaced with elephant friend. So that will be the first step. And elephant friend will not match with any one of those things. So it is a fail backtrack. So now I have this animal friend will try to match with this the other rule, because I have already explored this part. Now animal friend uh, will match with this one. So if this is true, if this can be true if and iter friend is true, so I will check whether this is true or not, and this is the ground truth. So I have an empty query, nothing to check. So uh, it will say yes. So the thing is that it will first it will match in that order from top to bottom, and with that assumptions it will try to check whether the uh, whether it holds or not. If it does not hold, then it will backtrack and it will try with the other rules. So this is an example how the backtrack actually occurs. So here we have been given with a set of uh, rules and set of ground truths, and our query is p1. So what will happen? So p1, it will first check if I need to show p1 to be true, then effectively I need to show a1, and in a1 if I need to show, then I have to check for c1, and for c1 I just need to check d1. Now from c1 I come to d1, and there is nothing d1 here. So effectively it turns out to be false or no, rejection. Then I try with the other c1, which is d2. So again d2 will not match with anything, so it will say a kind of a rejection. It will go back, and then a1 has no other option to choose, but p1 has another option, which is the b1. So it will check with b1, and if I need to check b1, then I have to check for e1, and e1 is true here. So effectively this is true, and here this d3 is nowhere, it was checked. So this is the records, this is the tree will that will be followed. So p1 a1 c1 d1, then d2 false, it will go back, it will go back, it will go back to p1, it will check for other rule, and so on and so forth. Now if I add d b1 uh, if d3, then it can also figure out the other solution also. So if I add this part is okay. So once it finds a match, then it will go back and it will explore the other path. So 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 it's recursively it finds out all solution. And so the thing is, in the interactive interpreter, we have to type, so when type semicolon when it finds the solution, or when it asks whether it's some kind of a match or no match. Basically, even if it finds a match, we are saying that it is not the match, and try to find the other solution, which will find out effectively find out all the solutions. So uh, so for we have variables in Prolog, and we have to match all those variables, or how we can actually match this thing. So the purpose of having variable is to uh, uh, compute more than yes no answers, because we can find out which values to the variables will satisfy my predicate, or we can compress the program as well. So like we are specifying our rules and the ground truth in this manner, but this part can be made compressed by using a single rule, like if we write animal X if elephant X. So when matching queries in rule heads or facts, variable allow many additional matches. So that we will see. So effectively, uh, with variables, the matching part needs to be taken care of a little bit. So for example, like say we have this situation that we have seen earlier. So now when we try to match this one, so we have animal Fred, and so there will be a match of animal, and here is a variable X, and what we can do, we can make X to be bound to Fred, so that we if X is bound to Fred, then we can use this rule. So what do? We bound X to be Fred, and once we make X to be Fred, so this will a match, and then this animal Fred will be replaced by the rule body, which is the elephant X. So that we have done here. And so X is Fred elephant X, so it is effectively elephant Fred, which is true. So from this step, so I can remove this part, so I know this is true. Now what I need to check is animal Mary and animal Joe. Now again we apply the similar stuff. Animal Mary and animal X will match, and we can replace X with Mary, and and that is elephant X. So this X and this X are actually different. So so that we have to take care of. And again, so X Mary and X elephant eh, and animal Joe. So if we continue to do so, we'll see that it will match with everything, and finally we end up with an empty query. So here, when we are matching certain stuff, we check the predicate, and if it's a variable and we are trying to match with some known facts, then we bound that variable in order to have that match. So for operations with variables, we have to be a little bit careful. So the queries are processed as before, so rule and fact matching and backtracking, that will remain same, but only thing we can use these variables to help us to match rule heads or facts. So query predicate matches with a rule head or fact if the predicate name must match. So that we have seen, like elephant X can match with elephant Joe, but this cannot match with anteater Joe. So so the predicate name must match. So once the predicate names are okay, we have to check for the arity of the predicate. That means how many terms are there within the predicate. Like if I have a foo xy, then it can match with foo Joe Mary, but it cannot match with foo Joe or Fu, Joe, Mary, Fred. So if the predicate names and the arity matches, then each of the k terms must match. So for example, if I have foo t1, t2, t3 to match with foo s1, s2, s3, then t1 must match with s1, t2 must match with s2, and t3 must match with s3. So during this matching, what we need to do, we have to bound the variables in order to match. So these bindings are then passed into the new queries consisting of the rule body and leftover queries of the predicates. So variable matchings, we have already some idea. So in order to just summarize that stuff, so if both are constant, so two terms with variables match if both are constant. I identify numbers of the strings and are actually identical. If one or both are bound variables, then they match if what the variables are bound to are actually matching. For example, if like say x and Mary, where x is bound to the value Mary, will match. Similarly, x and y, where x is bound to Mary and y is also bound to Mary, then we can say that it is a match. And x and n, where x is bound to Mary, will not match. So which is pretty understandable. If one of the terms is an unbound variable, then they can match, and what we need to do as a part of that, we need to bind the variable to the term. So like say x and Mary, where x is an unbound match, then what we need to do, we need to bound x to be Mary. And x and y, where x is unbound and y is bound to Mary, this two can match provided we make x is bound to Mary. Similarly, the other more generic situation, like when x and y both are unbound match, then we need to bound x to y or vice versa. So in order to solve queries, what we need to do, we have to go for unification, we have to go for goal directed reasoning, we need to do rule ordering, and we have to apply DFS and the backtracking, that kind of stuff. Now we will see one of the important thing in Prolog is the processing of list. So most of the computations are organized around this list. So two key things that we need to do with the lists is we iterate over them and we build a new ones. So let's say we would like to check the membership of a stuff. So maybe something like this, that we can say member xy, so which is basically means x is a member of list y. So how we can define this thing using the list? So we can say x is a member y if x is the head of the list. So and there x is the head of the list, or I can say x matches with the head of the list, and there are some list which is any anonymous variable which we represented through an underscore. So if this holds, then we can say definitely x is a member of the list, or it's not necessary that the x will be the head of the list. So what we can say, we define in terms of kind of a recursive definition. So what we say that we have a list, we have something in the front, and we have the tail list, and x matches with the tail. So what we can say, so member x this list if x is a member of T. So if that is true, then I can say x is a member of list. We will see with an example in this stuff how we can actually interpret this one. But this is a kind of a recursive definition, like x is the head or x is a member of the tail list. Similarly, if I want to build a list of integers in the range between I and j, so which is the predicate built from, to, and the new list, so we can define in this way. So build ij list, so if I is greater than j, then definitely this list should be empty, and if it's not so, then I can construct the list is I can take the first part of this I, and the rest is being constructed from I plus 1 to j. So therefore what we are saying that build ij and this list to be true if I less than j and n is I plus 1, and I construct a list from n to j, and that I put in rest. So this rest and this rest will be same, and I just add I in the beginning, so that will be my complete list, and this list will give me the list of a list consisting of from I to j. So it's a kind of a recursive definition. So let us look into another example, that how we can specify concatenation. So concatenation of list we can specify in this way. So if it's a concatenation of empty list with a list, it results into the same list. Or if I try to concatenate a list x1, l1, l2, and l3, so effectively this concatenations is same as the concatenation of this one. So one thing to note here, like when we say like concatenation of L1, L2, L3, so this can be interpreted in this way, like L3 is the concatenation of L1, L2, L1 and L2, which is L3, or I am trying to figure out L3 or I'm trying to figure out L3 from L1 and L2. So my point is this: if somebody provides me L3, then I can check the validity, or if L3 is a variable, then I can construct the L3 for which this concatenation predicate will be true. For example, if I've been given this stuff, so here I have been given y, so my so so if I've been given this as a variable, then I would be interested to find out for which value of y this is true. And so the actual question is that does there exist a y such that this is true? Or if somebody provides me the y list, then I can just check the validity of that one. So both the way is fine. So now once we have this thing, and if we try to derive this y, then what we can do, we we take this list a and b, and we try to match with this one. So we have this x, we have this x, and we have this, we represent ab as x as a. So so we mm, represent in this manner. So there is a match, because if I make x to be a, so I can represent this one as x, and L1 is basically nothing but b, and then this part I can say as x followed by y1. So which is the kind of a match. So if so this is a match. So now if this is a match, then this rule will be replaced by the rule body, and when I replace the rule body, which is effectively the concatenation of L1, L2, L3, so it will be the concatenation of B with C and D with this Y1. Now I choose x equal to B, and again I can choose x equal to B. So in order to match with this one, because I have this B, and so it's B followed by an empty list, this will remain as it is, and I can make this to be uh, x followed by y2. So this is a kind of a match, this is a match, and now I have to replace this body with the right hand part. So effectively the concatenation of an empty list, cd and y2. And if we do one more step, then this rule matches with this one. Effectively I will get back y2 as cd. So if I have y2 as cd, then y1 will be uh, uh, so if I so y2 will be cd, and this list, this y1 that we have represented as xy2 will be bcd, and this x y x and y1 will be abcd. So in this way we can actually construct the whole stuff, or we can, so we can determine for what value of y this is true, or if somebody gives me a y value, then we can actually check whether that is true or not. So here are few examples that we can write, like if we want to add an element in front in a list, so xl, and we add x in front of the list. So similarly for delete x, I want to delete x from a list, x followed by tail, then it results into tail. Or when if it's not the if it's not the head, then if I want to delete x, then I can represent the list as y followed by tail, and it results into y into tail 1, because x belongs to this tail part, and once I remove that x, it will have a new list. And if I have this situation, then I have to delete x from tail, and that tail results into tail 1. Similarly, for if I want to specify sublist, so S is a sublist of L. That is true if I can say in this way, if S and L3 is if S concatenation of S and with another list results into L2, and L2 with concatenation to L1 result into L. So so we can actually specify this sublist using this concatenation. So similarly, if we want to describe the permutations, we can have we can define in this way. There are many ways, so this is one of the ways. So if it's an empty list, that results into empty list, and if I have x head and list, and this permutation can be it's a permutation of L, and I insert x in L1, and to get a new permutation, to get the permutation P. So, and I have to define the insert also. So this insert is nothing but inserting an element in every place of L1. So so if I ask my tool like a permutation of something like this, if I say P of A, B, C, D, if I ask if I give this thing to my tool, it will generate all the permutation of A, B, C, D. And maybe you can work it out as an exercise how this will be generated, maybe with 3 variables, and then you see that uh, if you work out by hand, then you will understand that how it's actually working. So you can generate the all the permutation, or the other thing that you can check, like say if somebody gives me ABC as the list, and the permutation that I want to check is, let's say, B, C, A, whether this is true, this is a permutation of this one or not. So that we can actually check also. And if and if somebody, let's say, add another D, then definitely it will not match. So this for this different scenario, if you work it out by hand, then it will give you more insight how it's actually working. So with this I will stop. Maybe you can explore a few more examples and work it out by yourself. Write at least one program in G Prolog and try run that program, check for different queries. Thank you so much.